Imagine a place in the cosmos where gravity is so powerful, not even light can escape. This is a black hole, a region where the laws of physics are pushed to their limits. Black holes are invisible, yet their influence shapes galaxies and the universe itself. They're not holes, but matter crushed into an unimaginably small space, a gravitational well so deep, nothing returns. Born from the death of massive stars, black holes are the ultimate expression of gravity's power. For decades, even Einstein doubted their existence, but evidence forced us to accept these cosmic enigmas. Black holes are where general relativity and quantum mechanics collide, challenging our understanding of reality. What happens inside? What becomes of what falls in? These questions drive the search for a unified theory of the universe. Black holes aren't just objects, they're mysteries, daring us to push the boundaries of knowledge. They are the universe's most profound questions waiting in the darkness. Black holes begin with the death of massive stars, giants far larger than our sun. Inside, nuclear fusion pushes outward, while gravity pulls inward, locked in a cosmic battle. When the star's core fills with iron, fusion stops, and gravity wins in an instant. The core collapses, triggering a supernova, an explosion so bright it can outshine a galaxy. If the star is massive enough, the core keeps collapsing, crushed into a point of infinite density, a black hole. Imagine compressing Earth into a marble. Its gravity would be so intense nothing could escape. This is what happens to the core of a dying giant star, but on a cosmic scale. Black holes are gravity's ultimate victory, tearing a hole in the fabric of the universe. They are born from destruction, yet become powerful engines shaping galaxies. The death of a star gives birth to one of the universe's most mysterious objects. Black holes are the final act in a star's life, but the beginning of a new cosmic story. They remind us of the immense power hidden in the universe. To understand a black hole, look at its two parts, the singularity and the event horizon. The singularity is a point of infinite density, where physics as we know it breaks down. All the star's mass is crushed into a space smaller than an atom. Surrounding it is the event horizon, the invisible boundary where escape becomes impossible. Cross the event horizon, and not even light can return. Gravity here is overwhelming because all that mass is packed into a tiny space. The closer you get to the center, the stronger the pull, becoming infinite at the singularity. The event horizon marks the point where gravity's grip is absolute. For a sun-sized black hole, this boundary is just 6 kilometers across. For supermassive black holes, it can span our entire solar system. Black holes are simple in structure, but their effects are profound. They are the ultimate demonstration of gravity's power. Einstein showed us that gravity is the warping of space-time by mass. Picture a heavy ball on a stretched rubber sheet. Smaller objects spiral in, just like planets orbit stars. A black hole is a mass so dense it creates a bottomless well in space-time. Once you cross the event horizon, space itself falls inward faster than light. The size of this boundary is called the Schwarzschild radius, determined only by the black hole's mass. It doesn't matter what formed the black hole. Only mass, spin, and charge remain. Black holes erase their past, leaving only these properties. Time itself slows near a black hole, a phenomenon called gravitational time dilation. Clocks near a black hole tick slower than those far away. To a distant observer, someone falling in appears to freeze at the edge, fading from view. Black holes warp both space and time, creating some of the universe's strangest effects. They are the ultimate test of Einstein's theories. Once just theory, black holes are now proven realities, common across the universe. Cygnus X1 was one of the first discovered, a massive, invisible object orbiting a star, too heavy to be anything but a black hole. At the center of most galaxies, including our Milky Way, lurk supermassive black holes. Ours, Sagittarius A*, is 4 million times the mass of the Sun, anchoring our galaxy. We can't see it directly, but we track stars whipping around it at incredible speeds. In 2019, the Event Horizon Telescope captured the first image of a black hole's shadow in galaxy M87, a cosmic giant 6 billion times the Sun's mass. This image confirmed Einstein's predictions and stunned the world. Black holes shape galaxies, influence star formation, and drive cosmic evolution. They're not just vacuum cleaners, but engines of change in the universe. From stellar mass to supermassive, black holes are everywhere, fundamental to the cosmos. They are the dark hearts of galaxies, and we're only beginning to understand their role. Black holes have transformed our view of the universe. What if you fell into a black hole? To distant observers, you'd appear to freeze at the event horizon, fading away. But for you, crossing the boundary would feel uneventful, until gravity's tidal forces stretched you apart in a process called spaghettification. You'd be pulled into a stream of particles, crushed toward the singularity. Even black holes aren't eternal. Stephen Hawking showed they slowly evaporate, leaking energy as Hawking radiation. This process is incredibly slow. A stellar black hole would take longer than the age of the universe to vanish, yet it means even these cosmic giants will eventually fade away. Black holes are where our understanding of physics breaks down, pointing to deeper truths. They are paradoxes, destroyers and creators, mysteries at the heart of reality. As we study them, we push the limits of knowledge and imagination. Black holes remind us the universe is stranger than we can imagine. In their darkness, we find the edge of understanding and the promise of discovery.